parallel with the updates. So you have a string, you're constantly updating, and you want to do real-time analytics, so you constantly want to do queries. So the current approach is to use locks also for the queries, which might be very slow, or more commonly used in the absence of concurrent sketches is to update in epochs. So you load the sketch in one epoch, it just looks like that. You have two sketches, one is being updated, one is being read, and, one is being updated and one is being read, and the data that you get is inherently not fresh. You don't get the update fast enough, it depends on how fast you switch between the new one and the old one. So, basically the idea of concurrent data sketches, and I hope you got this animation, this is supposed to show that we take the logo of the sketches library and make it concurrent. That's the first result we have in this vein. It's a paper from PPOP 2020, also later appeared in a journal. So basically, I guess I went over all of these things, but we want to get high throughput, we want query freshness, we want it to be easy to use, so users don't have to worry about locks, they just have a library, and this is important for an open source project. And to continue to enjoy all the benefit of the sequential sketch. So this is a general architecture which is generic. It says give me whatever sketch you want, your favorite sketch. And what we're going to do is we're going to add some buffering before we use it. So we're going to take a global instance of the sketch. Okay, this is the global sketch here. And that's the one that's going to be queried. And for now, let's just say it's queried with an atomic snapshot that gets the consistent state of the current sketch. And then we use some buffering where we have basically small sketches doing exactly the same thing as the big sketch and periodically being merged into the big sketch. I'll talk more about the snapshots later. So here's an example. We have the theta global sketch and we have the buffers of size 2, so the buffers fill up. You know, the operations go to the local buffers, they don't go to the global sketch. And as the buffer becomes full, we invoke the merge operation, we put it back into the global sketch. And then we empty the global sketch. So that's the basic idea. Okay, and you see that when we propagated, I don't know if you noticed this, when we propagated the lady in the red dress from the right sketch, she was already in the global sketch, so we eliminated the duplicate. So we do the sketching again when we merge, we remove some of the properties. So the big question is, is it still fast? Okay, remember what made it fast? What made it fast? Yeah, there was no else, right? When was there no else? When theta was small. Okay, so you have to be careful here. Because we have this query about theta, we have this question here in the local sketch. We have to make sure the theta there gets small. Okay? So we make sure that even though we are emptying the local sketch, we're not resetting the theta to 1, because otherwise we would be slow. And beyond that, we want to learn from the global sketch, because the global sketch theta is going to become smaller faster because it has many local sketches. So what we add is some feedback from the global sketch to the local sketches to tell them that theta is non-error. So the local sketches can filter with the theta of the global sketch. And so that's one optimization we add. And the second optimization is we do double buffering just to not be idle when we're propagating, because the propagation takes time. So the way it looks is like this. The local sketch is actually 2 buffers. And when we propagate theta back. So the local sketch will use the global theta, and then it will do very few operations. We will not retain things that the global sketch doesn't need, basically. So that's the optimization. How did we affect the space and the error of the global sketch? So in terms of the space, some extra space in the buffers, right? We added extra space. And now how do we influence the error? So what is the impact here on the error of the sketch? It's, I think, pretty easy to see that we are undercounting, because the global sketch sees a subset of the stream, and it's undercounting. So it might miss some of the elements in small sketches. It might undercount. Problem we encountered: as the stream gets big, the buffer size is negligible, the undercounting is negligible, the impact on the error is small. What happens at the beginning when the sketch is small? And it's not just at the beginning, because the way these sketches are used is that many of them are used, and some of them will be small, some of them will be big, and they don't know a priori which ones will be small and which ones will be big. So we needed to find a solution for the small sketches, and what we did is for the small sketches use eager propagation, not to use the not to buffer through the sketch. Okay, so as long as the stream size is smaller than some threshold, we propagate to the global sketch. So in order to get good performance, we used an algorithm with very few fences, very few synchronizations. Even though we send information back and forth between the local sketch and the global sketch, we really optimized it for minimum synchronization. Because we're using all these local buffers, we can make it cache and NUMA friendly, like locate the buffers close to the threads that fill into them. And just make sure that we use enough sharing to get the good performance. If we share the theta, we get the performance that we need. So just balance the minimize synchronization and globalization, but share what you need in order to get the good performance, which in this case of the theta sketch is theta. Some results. This is performance, not surprising. If you have a lock base, you stay on the red line because you can't exploit more threads, but once you do it concurrently, you can go performance scale pretty well. Then the interesting question is, what can we say about correctness? And here again, I want to reiterate that we're implementing a generic sketch. The implementation is theta, but the algorithm, the theoretical part of it, is a general sketch. And what we want to show that the generic algorithm, when you instantiate it with your favorite sketch with any property, what impact it has on the error. And the impact that it has on the error is the buffering. And this is formally captured by a property called R-relaxed linearizability by Hensinger et al., which is a very cleanly and formally defined way to quantify the divergence from linearizability. So we can prove that we implement an R-relaxed linearizable sketch, strongly linearized. I don't know if you're familiar with the term of strong linearizability. How many people are? No? Okay, good. So not everybody, but some people. So strong linearizability, what you need to know for the sake of this talk is that if you want to use linearizability for randomized objects, it's not good enough, and you need to use a stronger version called strong linearizability, but I'm not going to get into details. Ask me about it later if you want. But the fact that you use coin flips makes it necessary to use a stronger notion of linearizability in order to get the property that replacing an atomic object with a linearizable one preserves the property. So you need a strongly linearizable one. So we proved that we satisfy our relaxed, stronger linearizability with respect to the original sketch. So now all we need to do in order to analyze a particular sketch is to analyze the impact of the R relaxation on that particular sketch. And that's what we do. We derive the error bound we take the relaxed specification, which is now a formal definition, a formal mathematical definition, and we prove, quantify how much the error is affected by it using some statistical measures. Yes, and so again, strong linearizability has the property that this is the error of the sequential sketch. Because if you take a sequential sketch and replace it with an R-relaxed, strongly linearizable one, you get an R-relaxed sequential one. That's the property of strong linearizability. This is just an illustration of the error. In the paper we have the equations, but basically what you get is you get, not surprisingly, a shift of the distribution. So if the estimate was some kind of a distribution, now because we're undercounting, the mean is shifted, and we want to get the mean is going to be smaller, but the standard deviation, the error, is going to remain the same. So the shape of the curve is going to remain the same. So that's the analysis we do, and just to try to see how this looks in a real implementation. Again, the implementation is with the theta sketch. The next graph, I'm going to rotate the axis. So think of the x-axis, which is the values as going on the y-axis. So now the error, this line, the zero line, is the mean, and everything is the error above it and below it. And this is a measurement of the error using our implementation. Why do we have no error at the beginning?
Buffers are not full.
Eager propagation. We do eager propagation when the sketch is small, so zero error. This is the threshold we determine. Once we hit that threshold, error starts. First it's big, and then it becomes smaller. Why does it become smaller? Because this is a relative error. As the stream becomes bigger, the buffer size becomes negligible. Why is it? Does it have a sawtooth shape? Because of the merges. Okay, every time you merge, you get better performance. And the error bars show you the distribution, because this is like error bars after running many experiments, and you see that it's pretty much the shape of the theoretical analysis that I showed you before. So, not surprising here. Okay, so great, got these generic solution, and we got throughput and freshness and ease of use, and we kept all the benefits of the small sketch, and that really ended our first paper. But and like I said, we contributed this back to the community, and it's available. You can go to Apache data sketches and you'll find it there. But then when we started looking at more sketches, then we realized that there were some challenges that didn't arise in the theta sketch, but might arise in other sketches that you look at. So yes, with the theta sketch, everything is fast. The small space, error, whatever, everything is great. But some sketches have slower queries. The theta sketch, the queries is a single read of an atomic variable, the theta. So this really synchronization is really not an issue. An atomic snapshot of a single read is a single read. Okay, so that's not a challenge. But if you use a different sketch, and I'm just going to give an example of one that uses a large array and you need to read the whole array, getting an atomic snapshot of that is actually costly. I'm assuming people familiar with the concept of atomic snapshot? Yes. Basically, you're trying to read the whole data structure in an atomic point in time. I'll give an example, maybe it's going to be clearer. So that's one big challenge that we had to address. And the second one is sketches that the merge is slower. That's another challenge we had to address, because on the theta sketch, the mergers are pretty fast too. So let's start with the first one. So this is the global sketch is strongly linearizable. The relaxation is only in the buffer. The global sketch is strongly linearizable, which means which means we have to get an atomic snapshot of the data structure. Let's look at an example of what a linearizable atomic snapshot is. This is just background for people who are not familiar with the concept. Let's say we have a counter that is multi-word. It doesn't fit in one word. So for this example, each word is a decimal digit, just to illustrate. So the first word is 0, second is 9, the counter is 9. Now we want to increment the counter to 10. This is not an atomic operation. We're going to have to change the first digit to 1 and the second digit to 0. If we read this during the change, we might read the 0 before the increment and the 0 from the second and after the increment, and get the value of 0 of the counter. So in order to make sure the counter is still monotonic, we need an atomic snapshot. So we need to be able to read both of these words in a common point in time. So that's just a simple example. Here's an example where it comes in a sketch. This is actually a really popular sketch by Graham Cormode and Krishna, and it's called the countenance sketch. It estimates item frequency. And this is, the sketch consists of a matrix of depth D and width W, and there are D hash functions that are used in order to hash elements into the sketch. So each one of these elements is a counter, and it's counting how many elements have hashed into this cell. So here comes the red lady, famous red lady from before. We're going to apply hashes 1, hash 2, hash 3, hash 4, hash 5 to her, and increment the hash range is the width. So we're going to increment the counter that the hash tells us to. So if H1 is going to be 1, we're going to increment the first counter. And then H2 is going to be 2, we're going to increment the second counter. H3 is going to be 1 again, we'll increment the second counter, and so on. Okay, so we're going to increment all the counters that she hashed into in the table, 1 in each row. And the query goes like that. When you query for an item A, you hash it 5 times or D times, and you take the minimum, the cell with the minimum counter. So, for example, in this case, in this case, the minimum counter is 2, okay, because one of them is 2. So it's very easy to see that this thing never undercounts, because every time we encountered the red lady, we incremented all of these, and when we query for her, we're going to find them. And because we use many counters, we get the statistical property that we don't overcount too much because of collisions. So basically, this is the analysis from the Cormode and Krishna paper. But the important thing is that we have the f hat is the estimate, so the f hat is never an undercount, and probability at least 1 minus delta, it's overcounts by most epsilon times n, where n is the size of the string. That's the property of the sketch. And this sketch is widely used. Well, now we ask ourselves, we want to implement it concurrently. And if we just read the counters, it's going to be very fast. We have 5 counters to read. But if we want an atomic snapshot, there's a performance penalty involved in that, because atomic snapshot either requires us to stop all the updates or to do some very complicated multiple iterations and store history and so on. So just reading the counters doesn't give us a linearizable value, right? Because if we read the hashes while they're being updated, we're not going to, we might return a value that doesn't occur in any linearization, because we saw some updates and we saw some later updates and we missed some earlier ones. And this is an example with multiple updates concurrent to a query. There's also an example, multiple queries concurrent to an update. Not going to go into that, but the point is that this is not if we just read the counters, it's not an atomic snapshot. So we wanted the sketch to be strongly linearizable, the global sketch to be strongly linearizable, to make it indistinguishable from a sequential and atomic counter. But this and preserve the balance, and everything will be good. But this requires something very costly. And we want something generic that would hold for any sketch. We don't want to open the black box and say, well, for this sketch it would be okay if we just read the counters, but for something else it might not. But if we look at this case, that's not what we want to do in the general sense, but just to get the intuition, we look at this case and say, well, what happened if we just read the counters, right? It would not be strongly linearizable, but what would happen? And we know that what would happen that is that if the query would happen atomically at the beginning, then it would turn some FS, I marked it FS because it's like F start, something that is the start of the transaction. If it would happen at the end, it would get something called FE, which is end of the transaction, which has some learning. And it happens somewhere in the middle. It happens somewhere in the middle. It doesn't match any linearization. But what we do know is that the counters are monotonically increasing. So we know that whatever number we get, we're trying to get the minimum of a set of counters. Whenever, because they're all monotonically increasing. So whatever number we get, even though it never happened in any linearization, okay, it's between F start and F end. It's some value that is at least as big as what we would have gotten had it atomically happened at the beginning, and not bigger than what we would have gotten had it atomically happened at the beginning. In other words, the estimate we get still has the properties that we want, because it's still bounded by the error, by the error, the item's frequency at the beginning, and the error of the sequential sketch at the time of the end of the query. So even though we didn't get a linearizable, we got a value that was never true. We got a value that is bounded between two legal values that we were allowed to return. So we didn't increase the error at all by not getting an atomic solution. Okay, so we get exactly the same number, 0 by looking for it. To capture this behavior, so this was just an example, so to capture this in a generic way, we introduced a concept called intermediate value linearizability. Intermediate value linearizability is a correctness criterion for quantitative objects. It's not for like general objects. You have a quantitative object that you can assign a numerical range to, or some well-ordered range to it, then some totally ordered domain, then you can implement it cheaper than linearizability. And actually in the paper we give an example where it's inherently cheaper. We show when there's a lower bound of linearizability, and we show a more efficient solution for snapshots. So it's cheaper than linearizability, and the important thing is that it preserves the error bounds. And it's also a local property. It's like composable and has other nice properties. So here's, just to take a step back from the coherent sketches, just to talk about intermediate value linearizability, to explain the general concept. So let's say I have a counter that is incremented in batches, okay? So I had this counter, it was 17, I added 4 to it, I added 3 to it, and then it became 24. So the only legal values in linearization are what? 17, 21, 24, right? That's it. These are the only legal values. IVL, intermediate value linearizability, says, okay, you do a query during this range, you can return anything between 17 and 24. Okay? Not limited to 17, 21, 24. You can return 22. You can return 20. You can return whatever you want. Okay? This is the general concept. The concept says that we're relaxing linearizability. It doesn't have to be a linearization. What there have to be is 2 linearizations that return valid values, and your value is bounded between them. So anything bounded between 17 and 24 is legal. The strength of this property is that it allows you, it's like linearizability in a sense, allows you to use objects with an arbitrary sequential specification. So this strength of this concept is it's useful for any object with this packed property, epsilon delta, probably approximately correct property. Any object that you have that for an ideal value v, the query returns v bars, which that with probability at least 1 minus delta over 2, it overcounts by epsilon and by the same error. Other counts by epsilon. And we can give a million examples of this, right? The theta, the quantile, complement, whatever probably approximately correct object you want. If you have this is the main theorem, right? If you have an IVL implementation of it, then you have the same error pumps. You have an object that has the same property. This is, you took an object with this property, a sequential object with this property, you parallelized it to an IVL object, and you got an object with the same property. Okay? So this is like a way to linearize it, to parallelize things that are not linearizable, but they still don't increase the error. So if we go back to our counting sketch, now it's just safe to just read the counters, because that satisfies IVL, and that's actually easy to see that it satisfies IVL. IVL exemplified that before. And so that's the, I guess that ends that part of the talk about IVL, and I don't know how much time I have in order to talk about the other problem, or maybe that would be a good time to take questions on the first part.
We have 10 more minutes.
Okay.
We started 10 minutes late, so you have 10 more minutes if you want.
Okay, so maybe there are questions on the previous part, if not, yes.
The mic is
Yes, yes. Oh, you want to bring it?
So maybe I missed some part, but so the monotonicity is the required property for testing. But even if we are so this hat thing with ideal property is giving me a value within the error bound, but errors are now increasing somehow.
No, it doesn't. That's the whole idea. It doesn't increase because linearizability just says that there's a collection of values that are legal, okay? And it doesn't say there's a specific value that you will return because it depends on the linearization, right? You can linearize it anywhere in the interval. So there's a set of values that you might be allowed to return under linearizability because the linearization point could be at the beginning, at the middle, or at the end, right? Like in this example. In this example, there are 3 values you're allowed to return by linearizability, right? And then if you look at the error is a property that has to apply to all 3 of them. And IVL is bounded between 2 legal linearizations, so the error doesn't increase. Okay? It gives you more degrees of freedom, but within the same envelope of errors. Doesn't allow you can't give an error that is a bit smaller than all linearizations. So, okay? Doesn't increase. Yes?
So, but follow-up to that. So does linearization buy anything at all? You know, the fact that the bounds don't change
Yes.
is only because we're looking at worst-case performance. Is there any benefit at all to using this linearizability instead of this weakening?
So linearizability is defined for general objects, and this is only applicable to quantitative objects. But I would argue that if you use any quantitative objects, there's no reason to require linearizability. It's going to be harder to achieve, and it's not going to give you better errors. If your point is to try to get a numerical value within a specific range, linearizability already has a range where it can, a range of places where it can happen. So you stay in the same envelope. It doesn't, but it's important to notice it's not applicable if the object is not monotonic. It's not applicable if it's not numerical. It's not applicable. So it can't replace linearizability in general. And it actually complements linearizability in the actually full version of the paper. We show all kinds of specifications that you can do IVL plus sequential consistency, or things that allow you to deal with the non-quantitative aspects of the data structure along with the quantitative ones, so you can combine them. Yes.
One related question.
Yes.
So, in what context this IVL will not be applicable? For what kind of statistics? General statistics.
So if whatever is not monotonic, it doesn't work. That's like the biggest one.
Like increasing, decreasing.
Yeah. If you increment and decrement, it doesn't work.
Oh, okay, both.
Yeah. If you do both, yes. If it's not monotonic, if you can go up and down, then it doesn't work. It just works for monotonic values. So it has its place, and in the place where it's defined, I think it's clearly supersedes linear reversibility. It's clearly a better notion. It's cheaper and it gives you whatever you want. But it's limited, and linear reversibility has a broader scope. It's applicable to more types of objects. It's applicable to Qs which are not numerical at all. Right? And so I can't do ideal Qs. Okay. Yes. Yes. Yes.
So just one more question. So it requires monotonicity or even the lattice structure of the operation or of the data domains of the.
The lattice is monotonic. I mean, if you were, it doesn't have to be totally ordered, but it has to be monotonic. You can't go back down. You have to go. It can be partial order, but you have to be monotonic.
Okay.
No, actually, it has to be totally ordered, I think. You know what? I guess I'm not sure about that right now. Because here I wrote totally ordered domain, so maybe it does require total order, but it definitely can't go down. If it's a partial order, I'll need to think about that. Maybe we can check it offline.
Sure.
Okay. So I can just conclude. I don't want to. I just can. The IVL is the second paper, and this. What time is it?
You have few more.
Few more minutes. So I just want to mention that we also addressed the question of sketches with slower merges, and this is if the merge is not scalable, then you can't scale by adding more local levels. So if you remember the graph I showed you with the data sketch at the beginning, it looked like the purple line. It was scaling. And when we look at a quantized sketch, where it does a merge sort at every level, so it's pretty slow, then we see that we need more buffers in order to get performance. And as we have a small number of buffers, we're not going to scale. So in order to be able to scale it, we're going to need to do another solution. And this is an example of what a quantized sketch does, and this is how it works, and I'm going to skip that. But I'm just going to mention briefly that the architecture, this is in SPA 2023, that the architecture we used in order to make it more scalable is to both add another layer of buffering. So instead of just merging from the buffer directly to the global sketch, we have some kind of an intermediate layer. And this intermediate layer is NUMA local. So we put one in every NUMA node. The threads in each NUMA node synchronize more closely. And then less frequently, we propagate from the NUMA node to the global sketch. And then we also have multiple snapshot objects because the snapshot takes time. And okay, just give it. And we get good performance, and that's in SPA, but no time to get into that. So, conclusion, big data analytics is important. It has a market share. It's widely used, and as memory is getting bigger, CPUs are not getting faster. They're just becoming more of them. So concurrent processing is going to be important, and the challenges we address are efficiency, which we get by minimizing synchronization and sharing pertinent information. And the challenge of correctness, which have shown basically two techniques we use in order to prove correctness. One is the relaxation, which does increase the error, and that happens due to the buffering, and the other is IVL, intermediate value linearizability, which doesn't increase the error, but gives us a generic way to analyze, perform the error of a sketch that is concurrent but without any atomic snapshots. So that, yeah, so these are the three papers I mentioned, and thank you.
No more questions, I hope. Yes, thank you.
session.
వీడియోస్ న్యూట్రల్ కెమెరా నా దగ్గరకు వచ్చి న్యూట్రల్ కెమెరా రూమ్లో పెట్టి 3 days అవుతుంది.
So there is a session. It's not a copyright right now. Only session.
It is
Security and blockchain.
I think we have to get everybody back. There's a
Yeah,
session.
yeah. I think
There's a session now.
So yesterday I have shared the golden free. Plus order the
చెప్పు హోటల్ చెప్పు హోటల్ సూప్ అట్లా యా ఐ ఈట్ ఇంగ్లీష్. హలో ఏముంటుంది బ్రో పార్టీ లేదా ఎక్కడ 200 మంది ఫాలోవర్సా వచ్చే మా దగ్గర రేపటితో లాస్ట్ అన్న ఈరోజా 5 or 6 అయితే మీరు ఇది మీటింగ్ పక్క మొత్తం ఇదే కాదు అబ్బా ఇంకా బ్రో చెప్పు ఈవినింగ్ 7 అవుతుంది మరి ఇక్కడ 6 అయిపోయినా కానీ మేము ఆడికి వస్తాడు 7 అయింది. 6 వస్తున్నప్పుడు మనం ఇప్పుడు పగబడింది. నైట్ అంతా దాగు పొద్దున నైట్ అంతా ఆల్కహాల్ పొద్దున వర్క్ కాలేదు. ఈరోజు మేము బయలుదేరేదని పెట్టుకుంటాం 5 అయిపోయినా కానీ వాడడం 1.5 hour పడుతుంది కదా. ఓకే సంగారెడ్డి ఇంకో ఇది ఐఐటీలో అవి 1 డేనే కదా, ఇది 4 days. ఇది ఇట్లా ఎట్లా అంటే పొద్దున వస్తాం అనుకున్నాను మరి ఎట్లా అంతే వచ్చేంత వరకు వస్తాం. ఎందుకంటే ఇంట్లో మా ఆడవులు లేదు, లేకపోతే వెళ్ళి తీసుకునేవాడు. పక్కన ఆడుకోమ్మ.
Welcome to session 4 on blockchain and security. First topic here is by Ravi Kishore on perfectly secure message transmission, tolerating omission faults, possibility, feasibility, and optimality. Good morning, everyone. Myself, Ravi Kishore. Today I'm going to talk about secure message transmission. So let me introduce the problem. What is perfectly secure message transmission? So think of a large distributed network and two nodes are designated as sender and receiver. Now, the sender has a message and wishes to transmit to the receiver. But this network is under control of the adversary. The adversary can corrupt up to T nodes of its choice. Despite that, sender wants to send it reliably as well as securely to the receiver. Here, corruption means omission corruption. We'll see what does it mean. What is omission fault? Suppose a node is corrupted in omission fashion. That means adversary can crash it or adversary can just use drop. But however, as long as this node is alive, this follows the protocol code faithfully. And I'll present a few protocols which are phase optimal. So let me introduce what is a phase. A phase is nothing but a send command either from the sender to the receiver or receiver to the sender. Think of the network as a graph. So this path could be, the path from sender to the receiver could be very long. There are many hops. But still, when sender sends to the receiver, we consider it as one phase, even though it may take many hops. So, yeah, like at the same time, sender and receiver can exchange information in the same round parallelly. That is also allowed. Okay, few assumptions and what is the network model that we consider. Here, the message is coming from some finite field, where like if you have either we can send one single message which is coming from a finite field or a vector of size L where each message is coming from, each sub-message is coming from the field F. And all the calculations takes place in this field F only. And here the network we can model it as undirected graph or directed graph, and then in that graph we can model it as in the voice model and routing model. We'll see these variants. However, in all these network models, we assume that the network is fully synchronous. This is very crucial for designing our protocols. Moreover, we don't assume that S and R share any key a priori. Otherwise, if there is a key, as long as reliability is possible, security is trivial because already key is established. And moreover, we assume that the complete topology of the network is known to every player in the network, including the adversary. And here we consider the adversary is static but adaptive. So what do we mean by static? Once if node is corrupted by the adversary, it remains corrupted through the protocol execution. Adaptive means adversary need not to choose these key nodes to corrupt at the starting of the protocol. As protocol progresses, adversary can, based on the communication it sees, it use drops, it can choose what nodes to corrupt and what not. Okay, why to study PSMT? What is the motivation? See, if you look at multi-party computation protocols, they assume that the network is complete. That means between every two parties there is a secure channel. However, that's not the case in the reality, right? So, what PSMT allows us is, even though between two nodes there is no direct edge, but this allows us to simulate that secure channel with the minimal connectivity. And what else? What is why we want to study PSMT specifically tolerating omission faults? I mean, if you notice, if you assume that every fault is Byzantine fault, that is much powerful. The adversary can deviate from the protocol code as well if the node is corrupted in Byzantine fashion. In that case, maybe with light connectivity, we are able to design protocols if we assume that the adversary corrupts nodes in omission fashion, whereas if you assume that every node is Byzantine fault, if adversary corrupts every node in Byzantine fault, then it demands higher connectivity. That means the protocol that designed for the Byzantine faults we can't employ to tolerate these omission faults because we need higher connectivity. The network may not have the required connectivity. Okay, our contributions are multifold. Let's start with undirected graphs again. Look at this graph. There are two disjoint paths between S and R. That is, one is passing through V1, the other one is passing through V2. Here the network is abstracted as undirected graph. That means if A can communicate with B, B can always able to communicate with A. In this setting, there are optimal protocols exist in the literature. However, those protocols, the best known protocol runs in 4 phases. Here, when we restrict it to ocean case, we are able to design 2-phase protocols. At the same time, guaranteeing that these protocols are communication optimal. And then in the wires model, what is wires model? Now the network is abstracted as a collection of disjoint paths from sender to the receiver and a collection of disjoint paths from the receiver to sender. So the paths from sender to receiver are known as forward channels, and the paths from the receiver to sender known as feedback channels, because once sender sends some information, if there something happens, then using feedback channels, receiver will be able to, may be able to communicate with the sender. That's why these are called feedback channels. Here the assumption is that the feedback channels and forward channels, they are disjoint, and within forward channels and within feedback channels, they also disjoint. No, there is no mode in common, of course, except SNR. So in this setting where we given a characterization, that means what is the possibility, under what conditions it is possible, and under what conditions it is impossible. And we are able to design optimal protocols. So phase optimal protocols, and then in some networks we are able to give a protocol which is phase as well as communication optimal. Further, if you look at the undirected graph setting, then where the protocol is 2-phase or 3-phase, or like as long as it's multi-phase protocol, we need the same connectivity. But whereas in the wires model, we are able to show that for 2-phase protocols, we need higher connectivity as comparatively 3 or more phase protocol. Yeah, as we said, like some networks where 1 phase is not possible, obviously the best protocol we can give is 2-phase protocol. In such networks, we are able to give 2-phase protocol whenever 2 phase is possible. And at the same time, we are able to give, when we ask is it feasible to give efficient protocols, of course yes, we design protocol, but with linear communication overhead. However, if we are in trade-off with the phase optimal, let's say instead of 2 rounds, if we can go for the 3 phases, then we are able to design a protocol which runs in 3 phases, at the same time guarantees the optimal communication complexity. Let's move on to the other contribution, which is in routing model. What is routing model? How it is different from the wires model? In the wires model, forward channels, feedback channels, they should not share any vertex in common. But here, we let that happen. Like if the path from the sender to the receiver and path from the receiver to the sender, they can share vertices. But what is the motivation for studying the routing model and why the name? So imagine, suppose except the sender and receiver, every node in the network is just a mere router. Okay, it can't do any combinations, but it can store and forward the messages to its neighbors. That's the only thing these intermediate nodes can do. So then, in that case, it's in the given distributed network, we can just abstract it as a collection of collection of paths from the sender to the receiver and receiver to the sender, because every piece of information originates at the sender or at the receiver side, because the intermediate node just forwards. So that's the motivation. So in this setting, we are able to give the characterization. That means under what conditions it is possible, what is the necessary sufficient condition for PSMP possibility, and we are able to design 3-phase communication optimal protocol. Okay, as I said, multi-phase protocols exist, but those runs in 4 rounds. These are the existing results. So whereas here we are able to give phase optimal protocols, at the same time guaranteeing that communication optimality. Okay, let's start with the existing results from undirected graph setting. So whenever I say PSMP is possible throughout this talk, it means PSMP tolerating T omission faults. Okay, so PSMP is possible between S and R, because we are calling between, because we are saying between, because undirected graph setting. whenever PSMD is possible from the sender to receiver, obviously the same paths exist between the receiver to the sender or from the receiver to the sender. So PSMD is possible from receiver to the sender as well. Okay. So the existing result for single phase is PSMD is possible between the sender if and only if there exist 2T plus 1 vertex disjoint paths between the sender and receiver. The idea is simple. Suppose first you need to understand, because the adversary can corrupt any T nodes of its choice in omission fashion. That means it can crash or eavesdrop. Suppose first claim is this: no T nodes or no T nodes can have full information about the message. Otherwise, adversary by tapping those particular T nodes gets the full information about the message. So no T can have full information. So once we understand this, suppose there exists at most 2T disjoint paths between the sender and receiver. Now, assume this scenario, adversary has this strategy. What adversary does is, adversary simply cuts T channels. So in this case, the receiver receives information from at most T channels. But we know that these T channels can't have full information. So receiver can't reconstruct the message. So reliability, we cannot achieve reliability. That's the reason we need at least 2T plus 1 disjoint paths. And why is it insufficient? So let's say, we just borrow protocol techniques from the cyclic multi-body computation, especially Sharnick secret sharing scheme. Sender starts with some random T-degree polynomial and replaces its constant term with the message. And then sender sends 2T plus 1 points using these 2T plus 1 disjoint paths. And then because adversary can crash at most T paths, receiver will receive at least T plus 1 points on these 3-degree polynomial, which are enough to reconstruct the polynomial, and receiver takes the constant term as the message. However, because adversary can tap at most T channels, so adversary gets at most T points on this 3-degree polynomial, which reveals something about the any coefficient, in particular the constant term. So that's how we get the sufficiency. And the multi-phase protocol is PSMD is possible for multi-phase protocols if and only if T plus 1 disjoint paths exist between sender and receiver. Here how the protocols works. T plus 1 necessity you can simply see, because if there are at most T, adversary cuts all the channels, so reliability itself is not possible. So T plus 1 is anyway necessary. And why is this sufficient? Because T plus 1 channels exist between sender and receiver. Now, sender and receiver can talk to each other reliably. So, sender tries to send some information securely to the sender. And if something goes wrong, then receiver is able to inform the sender that, see, these paths didn't deliver the message. So then they can know that, okay, these are the faulty nodes, throw them away, and then you repeat this process. So, and then they know that at most T faults occurs. As soon as they find these T faults, you are left with the channel which is fault free. So you just communicate in plain form. Okay, these are the existing results on the lower one. We just have seen that for the single phase protocols, 2T plus 1 disjoint paths are necessary from the sender to receiver. That means if you want to send one bit information, one field element, you need to send at least 2T plus 1 field elements. That's the communication overhead. And for the multi-phase protocols, T plus 1 paths are necessary. That means if you want to send one field element, then we need to communicate at least T plus 1 field elements. That's the overhead. We try to design the protocols which meets this lower one. Okay, so as we said, we designed a two-phase communication optimal protocol. Suppose a graph don't have the 2T plus 1 connectivity from the sender to receiver, then obviously one-phase protocol is not possible. But assume that in the given network, PSMD is possible. So the best protocol that we can give is two-phase protocol. So our protocol achieves that, and at the same time, this meets the lower one. The idea is simple. Suppose PSMD is possible, then we know that T plus 1 disjoint paths exist between the sender and receiver. So sender, in the first round, sender tries to send, let's say assume that L is 1 for time being, or message just one field element. What sender does, what receiver does is, receiver try to send T plus 1 random numbers using these T plus 1 disjoint paths to the sender. Now, for sure, sender will receive at least one random number securely, because adversary can tap at most T channels, there is one fault-free channel. So now this acts as one-time tag, but unfortunately sender don't know sender might have received out of these T plus 1 random numbers, some random numbers, but sender don't have any clue which one is actually fault-free or secure. So sender simply does whatever the random numbers received from the receiver, simply adds all of them, and that acts as a key. But now sender masks this message with this key as m plus k and broadcasts it using all the T plus 1 to the receiver. But unfortunately now receiver don't know which random numbers sender received and how the which actually contributed to the key. So this is easy to answer, because what sender does is sender constructs a bit vector of length T plus 1, where ith bit is 1 if S received ith random number from the ith path. So now, because there is T plus 1 paths, sender broadcasts this bit vector to the receiver, and now receiver looks at that bit vector and then sees wherever there is 1, that means these are the random numbers sender received, and then takes the corresponding random numbers and adds it, gets the key, and then now unmasks the message. That's how the protocol works in 2 phases. Okay. How we are able to achieve the lower bound for the communication complexity? If you see in the first round what happens, just sending random numbers, that is T plus 1 random numbers. And then in the second round, along with this broadcasting the masked message over the T plus 1 channels, along with that, we are sender is sending a bit vector. But now notice, this bit vector is of size T plus 1. Irrespective of what the size of the message, this bit vector is just T plus 1 bits. This is just to say that whether ith bit is ith random number is received or not. So that's how like we are able to amortize. Because now instead of suppose your message contains L field elements, for one message you send T plus 1 random numbers, and you do this for all of them, but use only one bit vector while sending from the sender to receive. Okay, PSMT in the wires model. This is the second contribution, let's say. Now, just now we have seen T plus 1 paths are necessary from the sender to the receiver. And then suppose there exists T plus 1 disjoint path from the receiver to the sender as well. Then whatever is the protocol that we discussed will work for this case as well. So at the same time, if there are 2 T plus 1 disjoint paths from the sender to the receiver, then also protocols are trivial. You start with 3 degree polynomials and 2 T plus 1 points, right? So the non-trivial case is there are T plus 1 paths from the sender to the receiver, disjoint paths from the sender to receiver, and at most 2 T plus 1 paths, at most 2 T paths, and not more than T plus 1 paths from the receiver to the sender. Otherwise, in all the other cases, protocols are trivially exist. So we just focus on this case. And then what is the necessary sufficient condition in this case? So now, when there are K feedback channels, of course this K is bounded by T, upper bounded by T, then the necessary and sufficient condition for PSMT possibility is there should exist 2T minus K plus 1 forward channels. This again, like necessity, we can show that as we argued earlier, no T paths can have full information about the message. So if suppose there exists at most 2T minus K feedback channels, then suppose assume that adversary crashed T channels. So 2T minus K is nothing but T plus T minus K. Adversary crashed T paths, then left with T minus K forward channels and K feedback channels. So these T minus K forward channels and K feedback channels should have full information. That means T paths should have full information. That's, in that case, we lose the security. Okay, necessity is done, then how do we show the sufficiency? We design a protocol that achieves PSMT in 2 phases. Um, this protocol takes a little communication overhead, like linear communication overhead. Let's move on to the actual characterization, that is for the 2 phase, and if there is no phase restriction, then the necessary sufficient condition is suppose there exist k feedback channels, then the necessary sufficient condition is maximum of t plus 1 comma 2 twice t minus k plus 1. These many forward channels are necessary. Here, necessity just follows in the earlier lines, but sufficiency, because we designed 3-phase protocol, how it works is in 2 phases, sender and receiver tries to establish a key securely. If that is successful, in the 3rd round, the sender masks the message with the key and delivers. Because both agreed on the key, then receiver unmasks the message using the key. But if in the 2 rounds, if that is not successful, then sender will be able to identify if all the k feedback channels are corrupted. So now sender throws them those k false away and then left with t minus k false. Now you run simply runs single phase protocol because there exist twice t minus k plus 1 paths. Okay. So here also we're able to design an optimal protocol. Now let's move on to the routing model. So here, if you see, there is only one feedback channel from receiver to the sender, which is S to V1, V1 to V0, V0 to S. And when receiver sends some information to the sender, sender knows that if sender didn't receive, sender knows that one of the 2 nodes are faulty. But in that case, sender can't identify which one is faulty. That means, as per the Weiss model characterization, no protocol exists tolerating one fault. But actually, we can give you a protocol in this. So the idea is simple. When receiver sends some information to the sender, if sender didn't receive that information, then let's see if V0 receives the message from V1, then V0 informs whatever the information that V0 received from V1, passes that to S. If not, if V0 didn't receive, then yes, V0 informs us that V1 is failed and informs the S the same information. 1 more minute and finish. So suppose V0 actually failed, crashed. That's why S did not receive that information. Then S identifies that V0 is faulty. This S is able to identify this because we heavily rely on synchronicity. Because by this time, sender is supposed to receive, or this particular node is supposed to receive. If it didn't receive, then that means that node is crashed. So S is able to detect faults, which of them are cause the fault in that path. So that's the crash failure detection protocol. So now the characterization comes to this. 30 more seconds. Yeah. So characterization is we need at least t plus 1 disjoint paths, and then if there are at most k paths from the receiver to the sender, then any vertex cutoff size k, you remove that, then PSMT should be possible in the leftover graph tolerating t minus k paths. That is the necessary sufficient condition, and then whatever be the protocol that we gave in the Weiss model, we can tweak them using crash failure detection protocol to design protocols for the routing model as well, which achieves, which means the lower mode. But just that it takes 3 phases. We don't know if the same protocols can be designed, with the optimal communication complexity in 2 rounds. Thank you. Feel free to ask questions. So there's
also exploring the PSMT in partial synchrony and asynchrony settings?
At least the protocol that we designed won't work. Yes, that's one area we'll focus, but designing protocols in especially asynchronous networks is extremely difficult. Here when sender node didn't receive the information, we don't have any clue whether the node is crashed, that's why it didn't receive, or because of asynchronous, the channel is so slow that the sender or receiver particular node didn't receive the information.
Yeah, asynchrony is tough, but how about partial synchrony? Like with some time bounds, like at least you receive the message.
Whatever the protocol that we designed here will work for partial synchronicity if you put the upper bound, because you just wait until then, and then you are bound to receive, or like if you don't receive, you know that node is crashed. Okay, thank you. The next talk is by Kalash on enhancing security in smart contract wallets and OTP-based two-factor authentication approach.
Good morning everyone. My name is Kalash and I am going to present Enhancing Security in Smart Contract Wallets and OTP based two-factor authentication approach. The co-authors are Dr. Bisak Chandra Ghosh and Dr. Saurav Kanti Adya, and this is a product of Cloud and Smart System Services Lab from NIT Karnataka, Surat. So this is the entire outline of the presentation. What I am going to go through is, first I will make you understand about cryptocurrency wallets, the motivation behind it, and then we will go through the challenges and contributions. Then we will discuss about the proposed framework, how the implementation has been done, conclusion, and the future work, what are the future enhancements. So starting with the cryptocurrency wallets, what do we have is, so cryptocurrency wallets basically provides an interface through which you can do transfer of cryptocurrencies. It contains basically a public key and a private key, and what happens is that whenever a user initiates a transaction, so the wallet initiates the transaction, and using that private key from the public private key pair, a digital signature is generated. Now that digital signature is basically sent to the blockchain or broadcasted to the blockchain, and in the blockchain that signature and the address is verified by the blockchain nodes. Later the mining and the addition of the block in the blockchain happens, and the transaction is considered to be successful. Now just note the fact here that in this entire process, the signature validation and address verification done by the blockchain nodes, and the user who has initiated the transaction, this is validated through the signature verification only. So in this entire process, the user validation relies on that signature verification. And since for this signature verification, we have used the private key as the initial factor, so a leak of private key because of weak passwords or because of malware can lead to the attacker to be in full control of the crypto wallet. So this brings the motivation towards this entire presentation or in this entire research work, is that the amounts involved in the cryptocurrency transactions are quite substantial and high. For example, you can see this is the rate of 29 December 2024. So the market cap you can see of these cryptocurrencies are quite high. So even if the private key is leaked and the attacker can do the transaction from your behalf, then what will happen? This will leave crypto assets vulnerable to the fraudulent transactions without any means of prevention. And in this entire setup, our focus lies on the smart contract wallets, which are state aware. That means we can embed our spending controls and security measures directly into the smart contract. So the objective behind this entire thing is to basically develop a two-factor authentication mechanism for these state-aware smart contract wallets so that we can securely manage the crypto assets and protect against the unauthorized access. So currently in this existing framework, what we are having is this, there is only one factor which I discussed about the digital signature in which we use the private key. But what we want to achieve is, we want to add a secondary factor. Against that existing primary factor, we want to add one more secondary factor to give the entire framework a more secure model. So the challenges for this entire framework is that, so when we consider the normal two-factor authentication mechanism in the traditional setup, where we have normal web application, so in that case, there is a server and there is a authenticator. In that case, what happens is that a normal seed is shared between the authenticator and the server, and based on the seed and the counter, the OTPs are generated and validated. But in our case, where we are using the public blockchain, even if you try to store a seed on the server, since in case of public blockchain, it is a public ledger and the blockchain transactions are publicly visible in the transaction pool. So in that case, everyone will be able to see that seed, right? So this is the first challenge. The second challenge is that you can't basically store the seeds on the blockchain, and that is how we can't use those traditional authentication setup methods. And also using conventional asymmetric cryptography techniques will result in computational overhead, because what do we have? We have a gas limit in case of the blockchain methods, which will, and because of those gas limits, if we use these asymmetric cryptography techniques, this will lead to higher execution costs. Also, submitting OTPs via the smart contracts is vulnerable to front-running attacks. As in, what happens is that if you try to submit the OTPs via smart contract, this will allow the attacker to intercept and prioritize his transaction against the transaction which we initiated. So the contribution in this entire research work which we have done is that we have proposed a smart wallet framework which basically provides two-factor authentication for blockchain transactions. We have introduced a secondary factor which I showed in your earlier diagram, which is based upon hash chains. That is what we are doing, is that we are adding a hash-based cryptographic construct to generate the OTPs. And to mitigate the front-running attacks, what we are doing is that we are having a novel pre-commitment scheme technique in which we are sending the commitment before sending the OTP. And after doing all this, what we are achieving is that we are basically eliminating the necessity for the client storage space, and we are also reducing the proof payload while sending the OTPs to the blockchain. We are not adding the proof payload, which is done in the earlier methods like Merkle trees. So our entire methodology consists of 4 constituents. These are client, private key software wallet, authenticator, and the smart contract on the blockchain. So the first factor is the traditional public key authentication, in which I discussed about the digital signatures. That is the first factor. The second factor is the OTP, which we are generating using the hash chains. And consider the fact that all these fund transfers are basically conducted exclusively through the smart contract, in which the spending rules are encoded. So you can see the hash chain here. What is happening here, that we are taking a seed SK, and based on this seed SK, what we are doing is that we are hashing it k times, where our entire hash chain is having k number of OTPs. So assuming k value to be 10, what we are doing is that we are taking a seed SK, which is generated by the authenticator, and then we are hashing it. For example, since I have taken the value of k to be 10, we are hashing it 10 times, and to generate a root hash. And this root hash is stored on the blockchain. Now consider, whenever the authenticator generates the OTP 1, so what will happen in the first round, that since we have stored the root hash or the hash root on the blockchain, so the first OTP which will be sent will be OTP 1, which will be the OTP before the root hash. So what will happen is that in the first iteration, what will happen is this OTP1 will be hashed one time to be checked at the blockchain setup, and thus we can verify it. So in this entire method we are having two phases. First is the initial setup bootstrap, and in this bootstrap method what is happening at that we are initially having a private key pair at the wallet. Then we are generating the seed at client C, and this seed is sent to the authenticator. Later, the client based on that seed is generating the entire hash chain which I showed you in the earlier diagram, and the root hash is computed. After computation of this root hash, this hash chain and the seed is deleted at the client C, and what we are doing is that we are sending this root hash to the smart contract S. So to send this or to do this entire process, what will happen is that we will have again that digital signature method, so that that entire transaction will take place. So that is what will happen, that signed transaction will be sent by using the private key SKU. It will be sent to the smart contract S. There the verification, digital signature verification will happen using the public key, and the value root hash will be stored. And the event will be sent that we have stored the root hash to the client C. And in the second method where the operation execution will happen, again we are having the same model, in which what is happening is that the client is sending an arguments based, that is, this is the operation, I want to send this to address. So the address will be sent as an argument, or the receiver's address will be sent as an argument. Now this D value is just a counter, so the OTP will be generated as the authenticator, and this, as I discussed earlier, to mitigate the front-running attack, what we are doing is that we are sending the commitment before sending the OTP to the smart contract. So in the first method, what we are doing is that we are just sending the commitment. This commitment is nothing but the hash of the OTP, which is generated by the authenticator using that seed SK which we shared in the first phase. This commitment C is stored now at the smart contract. And after the storage of this commitment C, in the second phase, what we are doing there, we are sending this OTP T. And again, this OTP T is sent by the authenticator to the smart contract for the validation. It goes through the client and the private key wallet W, where private key wallet W just adds the digital signature to it, which is later validated at the smart contract S. And there, the validation of the OTP, first with the commitment is done, and then the validation of the OTP with respect to the entire hash chain is done, where we hash it one time to get the desired root hash. We hash the OTP each time to get the desired root hash, and we update that root hash with the current OTP value. And by this method, we achieve the entire process of verification and validation at the smart contract without storing the seed there. So the entire implementation, we have done it in Ethereum. These are the tools which we have used for the implementation, and this is the user interface which is created to do the entire process. Now coming to the results, so there are four phases to it. First one is deployment and store value. This is one time. These all incur one time cost, whereas the init operation and the confirm operation will incur the cost each time a transaction happens. So whenever a transaction happens, first the initialization operation will happen, and then the confirmation of OTP will happen. And in these two methods are basically dependent upon the operation which we are invoking. Now coming to the payload cost comparison, as I discussed in the earlier approaches of the Merkle tree, what was happening that the payload is increasing with the increase in number of OTPs logarithmically. But in our case, in which we have used the hash chain instead of Merkle tree, the entire payload is consistent. That is, we don't need to send a proof along with the OTP. We are just simply sending a commitment which is taking some space, but in case of Merkle tree, we have to send the proofs of other nodes also to validate the OTP. In the second method, where we have the client storage, where we have eliminated the client storage. In case of smart OTP, we need to store the entire Merkle tree on the client side, where in our case, we don't need to store any tree or any hash chain on our side, because the OTPs are generated dynamically at the authenticator. So to conclude the entire presentation, what we have done is that we have proposed a simple system for two-factor authentication for smart contract wallets without storing the seed on the blockchain, and we have evaluated the entire setup by showing a constant payload size, and there is no client storage requirement. Even if we increase the number of OTPs, even if we scale up or we increase the size of the hash chain, there will be no significant impact on the payload size as well as the client storage requirements. So the future work that can be done, what we have basically implemented is kind of a HOTP mechanism for blockchain. What we can do is that we can also integrate a TOTP mechanism for our future work, as well as we can do a reduction in the OTP length, where the current OTP length stands at 128 bits. That is all. Thank you. Any questions?
So all the crypto wallets, whether it is Coinbase or MetaMask or Binance, they all have two-factor authentication. So how is your different?
No, in those all two-factor authentication approaches, this approach is quite different from that what you are asking. In case of MetaMask, what is happening that we are having a password which we basically put in to access our wallet, right? After accessing of the wallet, since the entire process is based upon your private key. But in our case, even after accessing of the wallet, if private key is leaked, in that case, this entire model basically gives you a strength towards storing all the cryptocurrencies which you have in your wallet.
And how do you think that private key will be leaked?
The private key can be leaked in case of malware attacks, or in case if you have used weaker passwords to basically encrypt your private key in the wallet. In that case, this model can be more functional and provide strength to the entire setup.
Okay.
Any other questions to Kalash?
So do you test it with some other public wallets like MetaMask and all?
Yes, the entire implementation is done using
No, integration. So I'm talking about the integration, not your local setups. Like,
No, this has been implemented on Sequoia testnet, and we have used MetaMask to integrate it.
thank you.
Let's thank Kalash once again. Next talk is by John Augustine from IIT Madras. It's on fair and representative jury selection for decentralized jury.
So thank you. This is joint work with my student Bhargavi, who could not make it. So it's primarily her work. But let me do the honors. Just to motivate the problem, we're talking about a situation where two parties engage in some activity, some work. One of them, let's say, as an example, provides some work to another person and in return for some remuneration. And the work gets completed, but there's a dispute. Party A is not happy with the work done by Party B, but Party B feels that they've done the work. So there's a dispute, and how do you resolve these disputes? This is something that occurs quite frequently in the blockchain context. And there are some solutions out there. There's one particular solution framework by Claros. In this case, they basically mimic the judicial system. So in this case, what happens is there is a pool of potential jurors. Every time there's a dispute, you collect a set of, you identify a set of jury members, and those jury members actually then, the two parties that have this dispute must then support all of their documents, provide all of their documents, provide evidence for why they believe that they are being wronged by the other party, and then the jurors have to analyze and then provide their verdict, and that's how disputes are arbitrated in these contexts. And so this is an established solution. We were just looking at this problem of this conflict resolution, and we thought with blockchain context, there might be a little bit more information that we can use to selecting juries. Because here, the jury is just chosen randomly. It has a huge benefit by randomly choosing the jury members. You make sure that it's fair to a large extent. But what the hypothesis we were having is, by looking at all the transactions that occur on the blockchain, we could potentially get a social network out of it. We know who is transacting with whom. That gives us some sense of who is closely related to whom. In particular, if you look at in a real-world jury selection, you don't want a relative of one of the members under dispute to be in the jury. You don't want co-workers. You don't want. So we stepped back and said, okay, that issue is not being addressed here. We can try to address it to some extent. And it's a completely decentralized environment. We have very little understanding of who's related to who, but we know who's transacting with whom. So if we have a social network that, or some transaction network, can we use that to make jury selection a bit more fair and just? So that was the context. So we formalized this problem in the following way. So let's say you're given a graph. This is the transaction network, and out of the set of all vertices in this graph, some of them are now eligible to be jury members. That's set B. And every time there's a dispute, and one thing to keep in mind is that this is not a one-shot problem. If you look at any of the classical, algorithms, one-on-one type problems, like for MIS, for example, or anything like that, it's a one-shot problem. Here, it's a repeated problem. Every time there's a dispute, we need to select a new set of jury members. So we have to select a jury set J, which is a subset of the eligible set, and it has to be of a particular size. And so our main contribution, in some sense, was like connecting this jury selection with the social networks and identifying some metrics under which that we would like to have in this jury selection. We performed some comparative analysis and provided some recommendations. And I do realize that I'm the one between you and your tea break, so I'm going to keep this talk short. I'll try to focus on some key takeaways from our work. The main takeaway is this: as I've said, this is a repeated algorithm. So you repeatedly choose the jury members multiple times, and fairness is so the specific aspect of fairness that we care about is we don't want certain members of the eligible pool to be overused as jury members. We don't want to ignore certain members of the jury pool either. So we want everybody to get a shot at being part of the jury. But there's also a structure associated with this. Remember, we are focusing on a graph and trying to pick jury members from that structure, a graph structure. So any algorithm that we design might specifically favor certain portions of the graph because it's very centrally located or something like that. So there's this balancing act that needs to be done. So our main approach was to have some fairness based heuristics and some spread maximization. So you want the jury to be selected so that it's well spread from the network. It's not concentrating on any one location of the network. And try and mix and match these two families of heuristics and to generate heuristics that might be good for the jury selection problem. And we have some candidate heuristics. So for example, one of the original Claros algorithm just did a random selection. So that is very fair in the following sense that everybody has an equal shot of being in the jury in every selection. So there is a certain value to it. So in the random seed, what we do is every time we select, we want to select jury members, some number of them are just going to be randomly chosen. That's the random seed. And after that, we apply the spread maximization heuristic to complete the jury pool. And that way, we have some spread in the network. It's not. It's just to give some coverage to the whole network. So these were that was just a sample candidate heuristic. For example, so the random candidate pool. So suppose you have a full graph. The candidate pool will first randomly select a much larger pool of eligible candidates. That will be chosen randomly. And then the spread maximization algorithm will be applied only on the candidate set. So again, these were two different ways to mix and match fairness and spread. Just candidate examples that I'm giving. We had some metrics as well for measuring all these criteria. How fair is it? How well spread within the network is the jury and so on. I'm not going to spend too much time on that. We basically have some recommendations as well. But in the interest of time, I think I have only about 5 minutes. In the interest of time, what I'm going to do is make a more theoretical, philosophical observation on a class of problems. So what we are used to in classical theoretical computer science, for example, if we are interested in, let's say, MIS, for example, we are focusing primarily on one-shot algorithms to solve the MIS problem. It could be, the sort of insight that I got in this context is, what if you want to repeatedly run the MIS algorithm or any other cluster or k-means algorithm or any of these types of algorithms that creates where the solution is a subset of the vertices of a graph. But then you want to do it repeatedly, and when you do it repeatedly, you want some fairness to ensure that the solution set is every time is sufficiently random and spread out over the set of possible solutions. So this is the philosophical issue that came up in this work, and that might be of interest to us theoreticians. So instead of thinking of these algorithms as one-shot algorithms, can we think of this as repeated algorithms where the selected set gives some guarantee that everybody, like for example MIS, if it's just a one-shot algorithm, we don't care about it. But repeatedly when we perform MIS, and let's say the members of the MIS are required to do some activity, if you overload some nodes in the network, that is unfair to those nodes. But if you repeatedly invoke MIS and you're able to guarantee that the workload gets spread, your chance of being in the MIS is neither too bad nor too less. That might be an interesting twist to the type of algorithms that we design. So that is the sort of the philosophical takeaway from this line of work. And so that's essentially it. But as far as this work concerned, we just we came up with a bunch of heuristics to ensure fairness. It was a sort of unpredictable choice of jury members. Made sure that the workload is balanced, but at the same time, the jury members are sufficiently spread as well. And future directions, one thing is definitely the theoretical. So this work is purely heuristics and experimental results. We would love to explore this more formally, and also explore this philosophical perspective on algorithm design in some other contexts as well. So thank you.
Do we have any questions to come?
So I was just thinking that if two parties are there and you want that no one who is related to them should contribute to the jury, so I thought that maybe we can use a network graph and simply exclude those nodes who they have been transacting with, and maybe to be more cautious, maybe one hop more or two hop more we can exclude.
Good point. That's a certain aspect that we wanted to care about, but the other aspect that I did not mention is also a demographic diversity. Suppose you have two people in dispute. It's not just that you want their immediate relatives or people to be excluded. You also wanted the jury to be selected so that it's well representative of the community as a whole. So that is, so if you have like a graph, this overall graph represents the entire society. So we want members of all parts of society to be part of the jury. So that was the spread maximization perspective that we took.
Yeah, I was just starting.
Yeah.
I was reaching there only.
Yes.
So like demographic, then one more thing was that like you were saying web application, the example that you were, that web application.
That was just one.
So how do you account for like who is actually, who knows web development? I cannot pick a random person and then ask them to arbitrate on a dispute that is like specific to.
Good point. So that one, so the entire set of vertices might be large, but for the certain class of disputes that could occur, we will have a different eligibility set. So if you recall from the formalization, the U is the set of all vertices, but B is the set of eligible vertices. And that will be based on the domain expertise, who has declared domain expertise in that particular area. So the types of disputes could be from a variety of domains. And based on that, the eligibility set will be declared first.
And last, you were saying that you do not want the jury to overwork. So how to ensure
the jury to
overwork means like it's a repeated process. You don't want the same jury to be selected time and again.
Correct.
One way is we can use some metric that some person has been used once, twice, third.
Correct. Exactly. That's as a metric, yes. So we do capture that as a metric, but the issues we don't have well-defined. At least I'm not aware of well-defined algorithmic paradigms that allow you to repeatedly execute these things so that the metrics are properly maintained. Because sometimes, by the nature of the problem, you do need certain expertise. So there's a tension between a good fairness as well as who has the right capability to resolve these issues. So this tension, basically we need algorithms that work with, that can handle working with this sort of tensions.
So how did you decide on the weightage?
In the interest of time, may I suggest that we take this?
Oh yeah, we're well past that. Yeah. we can maybe take this
Let's
off.
thank John again, and now there is a coffee break until 11:30. And Sandeep has some announcements to make.
Yeah, thanks for joining this session. So we are going for the break. We'll be back by 11:30. So request to all the authors who have not yet uploaded the presentation. So please upload the presentation to the Google Drive link that has been shared yesterday. Thanks. See you on Friday.
Okay, I guess we are all set up now. So, welcome everyone to the Mobile Agents session, where I'm happy to introduce the next speaker, Kaushik Mondal, who will talk about path-connected dynamic graphs and dispersion on those types of graphs. And this is joint work with Ashish Dakshin. Over.
So, I think I'm audible. Okay, so this is joint work with Ashish, and we are going to talk about different connectivity models on dynamic graphs, and then we will see that how the dispersion problem pans out on those different models. So first, what is a dynamic graph? So a dynamic graph is such that where the structure, the graph structure, vertices and edges may change over time. However, in this work we are considering dynamic graphs where only edges can change over time, and so we view this as it is over time. We view this as a sequence of graphs like G1, G2, G3, G4, GR, GR plus 1 and so on, where GR is the graph structure on round R. As we are in the distributed domain, from time to I am moving to rounds. Okay, and then here we say that the V is the fixed set of vertices, and the ER, which is the set of the edges on the particular round R, that is the edges of GR, they can be a subset of V cross V. Okay. So next, there are already two connectivity model over dynamic graphs. One was proposed by Kuhn et al. In 2010 in their stock paper, and another one was connectivity time that was proposed by Mikhail et al. In JPDC at 2014. So first we will see these two models, and then we are going to introduce another model whose strength is in between these two models. So this T-interval connectivity is like, as we are talking about a sequence of graphs over time. So if you consider any consecutive T rounds and look at the graph structure, then if you consider the intersection of the edges, they form a connected graph. So that is what we mean by T-interval connectivity. Sorry, here. So the intersection is connected. So if it is T is equal to 1, that means it is connected in every round, and not only that, T is equal to 1 means, let's say in round R, ER, the set of edges in the graph, they can thoroughly change in round R plus 1. ER plus 1 can be a totally new set of edges, but both are connected, GR as well as GR plus 1. But if T is greater than 1, then there is some constraint from the adversary's end who is relating the edges or adding the edges. So since T is greater than 1, if you look at a consecutive interval, the intersection needs to be connected. So a underlying connected backbone must be there that cannot be deleted by the adversary. So here, from this perspective, we can say that again, this T greater than 1 is little bit stronger model than T is equal to 1. That is, one interval connectivity is little bit weaker than T interval connectivity, as the adversary have constraints. And then this was another model, connectivity time. It is the opposite of the previous definition. It says that if you look at any consecutive T rounds, then the union is connected. So that means, of course, it is obvious to understand that at each round it may happen that at each and every round the graph is disconnected. So like here there is one example. So this is for T is equal to 3. This shows us one dynamic graph in the connectivity time model. So here we can see that, let's say in time 1 the structure is given in A, in time 2 it is in B, in time 3 it is in C, and again in time 4 it is A, time 5 it is B, and it is C, and so on. So you can see that at each round it is disconnected, but if you take any consecutive 3 rounds, the union is connected. Okay. So next we are coming up with this model, which is called T-path connectivity. So we say that if you look at T consecutive rounds, let's say from round R plus 1 to R plus T, then if you consider any two pair of nodes UV, there must exist at least one round where there will be a path from U to V. So here also, each and every round the graph can be disconnected. But there must be a path between any pair of vertices within any at least one round and within any consecutive T rounds. So if we go back to the previous example, we will see that this is maintaining connectivity time for T is equal to 3, but this is not maintaining T path connectivity as V1 and V4, there is no path in any of the rounds. So if we go to this example, this maintains T path connectivity, as we can see that if you choose any two pair Vi, Vj, there always exists path between them in at least one round for any three consecutive rounds for T is equal to 3. So then this is one observation that we can see that if it is T interval connected, it is definitely T path connected, because T interval connected means it is indeed connected in each and every round. So of course then in each and every round you have paths between any pair of nodes, it is T path connected. And T path connectivity means if in any consecutive T rounds there is path between any U to V, of course the union is going to be connected, so it implies connectivity time. So we can say that the strength of this model lies in between. Okay. So next we are going to the dispersion problem, and we will see that how it turns out in those models, and it is already studied in the one interval connectivity model. Okay. So this is the problem, as we know that there are k less is equal to n edges who are initially arbitrary positions on the nodes of the graph of G, and by the end of the algorithm, each node should not contain more than one agent. No node should not contain more than one agent. So here, if we see, this is not a dispersed configuration, as in V4 there are two agents A4 and A7, but this is a dispersed configuration as there is no more than one agent at each and every node. So now there are two types of dispersion. One is implicit, that agents may not terminate, the configuration will be dispersed, but agents may not know that okay, we all are dispersed and we can terminate. Other one is explicit, that each agent terminates knowing that the dispersion is achieved. So here, now I am going to the dynamic graph model on which we are going to look at these problems. Again, here we are not fixing the connectivity model because that will vary. So more or less, as we have said, it is kind of a sequence of graphs. It is varying over time, the edge set is varying. So then, again, the adversary which can add or remove edges arbitrarily at the beginning of round R, of course it has to maintain the underlying connectivity model according to the assumption. And then this GR means each of the graph, they are port level graphs, they are anonymous graphs, and the degree of any node is within the, the port numbers of any node are within the range 0 to degree V at the round R minus 1. And then there is no storage in the nodes. And what is the agent model? Again, there are k less equal to n agents placed arbitrarily on the nodes of the graph. Each agent has a unique ID in the range 1, k. So here I would like to say that, of course, the algorithm works if you take arbitrary ID range like 1 to n to the power c, but on the complexity, the n will come as parameter instead of k. We are using this model as this model is taken in that one interval connected graph which we will show. So we wanted to keep the same model here. And the agents are equipped with some memory, and the algorithm runs in synchronous round. In each round, an agent performs one communicate, compute, and move cycle. So communications, if it is local, so only agents who are at the same node can communicate between each other. And if it is global, that means irrespective of the position of the agents, if one agent speaks from a node, all other agents, wherever they are, they can hear what that agent wanted to communicate. and then there is zero visibility, so that an agent located at a particular graph node can see agent's pages at that node at around that and port numbers associated with node B, but it cannot see the memory of the other agents. Again, here it is not even required because we are having either local or global communication, so whatever information you want to pass, you can pass through communication, you don't require to see the memory. And for one-off visibility, what is happening? So if an agent is at node U, it can see all the neighboring nodes and the induced subgraph formed by that node and all its neighboring nodes, so that it can know. Okay, so this is the status of the dispersion on the model here. So this 12 is going to be basically 2, which is efficient dispersion of mobile robots on dynamic graphs by Kempton-Lee et al. Which came in ICDCN 2020. So it studies on one interval connectivity. It says that for both implicit and explicit dispersion, global communication and one-off visibility are necessary as well as sufficient conditions, and they solve with theta k time and theta log k memory per agent. So what we are providing in this work? So we say that in connectivity time model, whatever assumption you take global communication, you take full visibility, you give infinite memory, still it is not possible for the agents to achieve dispersion. And then for T interval connectivity, we have a small observation. For T greater than 1, as it is solved for one interval connectivity, as we have already discussed, that this T interval connectivity, it is a stronger model than one interval connectivity, as the adversary has somehow restricted, it cannot change all the edges the way it wants. So here, this necessary assumptions does not fit in directly. So this can be open question that are these global communication and one-off visibility are still necessary to solve the problem in T interval connectivity, whereas the sufficient conditions are the same as the algorithms works perfectly. So our main result is on this T-path connectivity model, where we are showing that for implicit dispersion, global communication and one-off visibility, they are must, and we are providing an algorithm with them as well. But for explicit dispersion, we see that along with global communication and one-off visibility, knowledge of T is also must to achieve the explicit dispersion where the agents can terminate. And then here we provide a omega kt lower bound over time for the dispersion, and our algorithm runs in order kt time. And then the memory for implicit is theta log k, and memory for explicit is theta log max of k comma t, as they know T, and we are somehow using that T, they need to store it, they need to need that memory. And again, one word on this regarding dispersion and dynamic graph, it is not there in this table. It was determining dispersion of mobile robots in dynamic rings. It was started by Agarwal et al. That was came in ICDCN 2019. So our impossibility results on connectivity time model, a set of k less equal to n agents can't solve implicit dispersion, even implicit dispersion, in the dynamic graphs which hold the connectivity time property. This impossibility holds even if agents are equipped with infinite memory, full visibility, global communication, and know the parameters k comma n. This proof is really very simple observation, we can say. So let's say, we are starting with k is equal to n many agents, and it can be very easily modified to any number of agents where k is less than n. So here what we are doing, so since initially it is undispersed, at least one node will be there where there is at least one node will be there where there is no agent. So we say that okay, you keep this node apart, and then in 0 to t minus 2 rounds, you keep all other nodes in a path, they are connected. So what you do after that, since there are n minus 1 nodes in the path and there are n agents, so at least one node with multiple agents will be there. So in the next t minus 1 rounds, you take that multi-node with multiple, you keep it separately, and you put that whole back in and make it a path. And you continue this so that a whole and a multi-node is always into disconnected components. So the dispersion cannot be achieved. So then next, let agents be equipped with global communication, one-off visibility and do not know N and K, this is on T-path connectivity. It is impossible to solve explicit dispersion in T-path connected graphs unless agents know T. So I am not going to the proof of this. And then we are going to this lower bound result that any algorithm solving implicit dispersion on any T-path connected graph of N nodes requires omega kt rounds, even if they are equipped with global communication, have full visibility and know all of K, N and T. And here the proof idea is very simple. Let's say left hand side is the graph initial configuration where S1R is a star, where each node contains at least one agent, and here S2R is another star where no node contains agents. So we are keeping them disconnected for T-1 round, and for one round we are making one connection. So what can happen in that one round? One node agent can come from that side to this side, so at most one hole can be filled. So in the next T-1 round, what we will do, we will take that node and we will put it in S1R. So again, S1R will be increased 1 by size and S2R will be decreased 1 by size. So in this way, you can fill one hole in T rounds, and then since you are starting with K agents, so you may need to fill order of K holes, and this gives you a omega kt lower bound. And then this is the existing algorithm which we are using from ICDCN for our algorithm. I will very quickly tell this. So their idea is that since you have global communication and one of visibility, and the graph is connected over every round, so what a node agent is doing, they are sending their one hop information to all other, and due to global communication everybody can hear, and since the agents have ID, so each node is now getting ID who are having agents. So in this way there will be, so and with this all the agents can have a map, they can calculate in their memory from a multi-node to a whole. And then what can happen, let's say from this node, this agent can slip to this hole, and from this node the agent slip to there, and here it was a multi-node in the previous figure, one agent slips there, and then in one round you can fill up one hole. So in order of K round, their algorithm terminates. So what we are doing in our algorithm, basically we are keeping just another parameter which is ai.t, and we are saying that at round R, if agent gets information of multi-node and as well as a hole, then they run the existing algorithm of their paper to fill up the hole. And then they are checking, an agent is checking if it is not hearing any information about a multi-node for consecutive T rounds, is the AIT value increase. AIT value increases, goes up to capital T, and they can terminate that they must have heard from a multi-node since the T-path connectivity model we are working on. So here the termination may be null simultaneously. So then this is the theorem that in theta kt round you can solve the problem using theta log max kt bits of memory per agent. And in synchronous setting with global communication, one of visibility and knowledge of T. And then, okay, for implicit you don't need the knowledge of T, as they can continue the algorithm of 2. Okay, so what are the future scope? The necessary assumption to solve dispersion on the interval connected graph is still an open question, and a similar study can be done on other problems such as exploration. Okay, so these are the references. Okay. Thank you.
Yeah, let's thank Kaushik. One quick question. If not, in the interest of time, let's move on to the next talk, which is also by Kaushik. So
work with Assis Saxena and Below. And here also, we are going to talk on a open problem provided in the same paper we are talking about, that's ICDCN 2020. And there, the author says that, so they studied on the one interval connectivity. Now, TVG is a much stronger model, which is time varying graphs, which we are going to see. So, what will be the status of this problem on TVG? Do we still require that kind of very strong assumptions like global communication and one of visibility and so on? So, we aim to answer that question here. So, again, these things are same, so I am skipping, this we have already talked. Here, something new is there. So, Moonlight was introduced another type of dispersal definition in TMC, where they were starting with more than n agents. And the definition says that let k agents be present in a graph of n nodes, n node graph G, and each node should have at most k by n sealing agents in the final configuration. So then the related work, again those two works only, that dispersion dynamic graphs, and it was 18, and the work by Empolani et al., where it is kept as open problem that what is going to be the status, that whether one still needs one of visibility and global communication to solve dispersion in a stronger model such as TVG. So let us check the TVG model, what are the main differences of the previous model and this model where we are going to work. So in TVG, so there we said that in every round the choice of edges by the adversary can be from V cross V. So they can take any edge as it want. But here in TVG, you already have a footnote G given at the beginning. So whatever be the edges are there in G, adversary can choose only from there. It cannot be chosen from outside. Now, if that G is a complete graph, then from this context, this becomes the same. That adversary can choose anything because the underlying footnote was a complete graph. Okay. So other than this, okay, again, adversary can remove edges from footprint G, keeping G connected at each round. So this is one strong assumption in TVG, that TVG must be connected, the dynamic graph at each round, GR must be connected at each round. And then the agent model is the same, except the last point, it says that an agent residing at a node V in round T knows delta V in the footprint of G. So it knows what is the actual degree of that node in the footprint G and all associated ports corresponding to the node V in G. So that means, let's say I am the agent, I am at the node V, and at round R I will see its degree as 7. Let's say 7 was the original degree in the footprint. Even if one edge is deleted, I will see all the 7 ports. So, and it does not understand if any incident edge of node V is missing in G at that round. So even if port 6 is missing, it is deleted, I will not be able to understand that. Okay, so this model is taken in this exploration by dynamic networks in Journal of Computer and System Science. So I think this is by Goto, Clocini and Nicolo. And then the communication model is same, local global, so skipping, 0 of visibility, 1 of visibility. Okay, so here is one point. If it is 1 of visibility is there, then what can happen? Then the agent can know about that missing edge, because what the agent see? It see all the ports, 7, but it see there are only 6 neighbors, and one neighbor, it does not see through one port, one neighbor is missing because that connectivity is not there in that particular round. So it understands that through this edge, this is missing in this round. So this is why 1 of visibility is very strong assumption with this model. Okay, so in 0 of visibility, agent cannot sense the missing edge. 1 of visibility, agent can sense through which port edge is deleted. So now, the problem 1 is the original dispersion problem, k raised to L agents, and here we are keeping a problem 2, which is with k greater than n agent, which was proposed in TMC to 2019. So then, we have some impossibility result. We say that it is impossible to solve problem 1 for any n greater is equal to 6 with the agents having 1 of visibility but no global communication, even if the agents are initially co-located and have infinite memory. And we also have the result that it is impossible to solve problem 1 considering global communication but without one of visibility. So here it seems like to solve k this is equal to n, the dispersion in TVG, again you need global communication as well as one of visibility. Okay, so actually our goal was then what do we need to remove those strong assumptions as to solve this problem on TVG. So from that end, we see that if we have one extra agent, that is n plus 1 agent if we start with, we will be able to solve the problem on TVG with only 0 of visibility and local communication. But this greater than n agent, it does not go with the problem definition of k is equal to n. So we also introduce that problem too, that if there are more agents, what you are doing. But here in this work, we are providing a solution that if you have n plus 1 agents, we are being able to solve problem 2 without any strong assumptions, so only in presence of 0 visibility and local communication. So very high level I will tell. So what is happening, a group of agents G1, let's say they are all the agents, start executing the depth first search algorithm. They all n plus 1 agents at a node. And at some point, due to some missing edge, they got stuck. So what they are going to do, they are going to divide it in 2 groups. Now, one group will stay on the exact path of the DFS and other group will distract the DFS to a different path. Now since the path is connected, so at least another path, another edge will must be there. And then what is happening, then the group is divided in 2 groups, and as I said, G1 stays in the original path and G2 is deviating. Now, if adversary does not allow to move G1, then G2 will be able to finish his DFS and by dispersed by 4n rounds or 4n square round we can say. So if G1 is stuck for 4n square rounds, it understands that G2 is dispersed, it can further divide in 2 groups. On the other hand, worst case what can happen, when G1 can move, if G2 can get stuck. So in that case, G2 counts that how many times I am getting stuck. If it finds that I am getting stuck for 4n square time, it understands that G1 moved at least 4n square time. So G1 has completed its dispersion and then G2 can divide it into 2 groups. So we want no more than 2 groups will be there in the system so that each agent who are settled at a node can give information only of finitely many DFS so that we can have the algorithm with order of log n memory. So this is how it goes, and then since at order of n to the 4th time we can ensure that G1 must be dispersed and G2 can be divided, so complexity goes to order of n to the 4 log n because this division can happen for order of log n times. So this is our final result, that algorithm solves dispersion on TVG with n plus 1 initially collocated agents in order of n to the 4 log n rounds using theta log n memory. So the one point is that our impossibility result hold for k is equal to n only, but still we can say that the problem is impossible to solve because we are giving one instance where it is impossible to solve. But it is really open to study that if what happens if k less than n, if one can come with the impossibility instance. One can look for more efficient algorithm for n plus 1 agents, and we are taking n to the 4 log n time. One can start from arbitrary initial configuration for n plus 1 agents, and one can study what can happen beyond n plus 1 because things are not straightforward. Maybe you can handle up to n plus delta v, where delta v is the minimum degree, but beyond that it requires further formal study. So these are the references, and thank you.
Thanks again, Kaushik. Any questions?
Directed graphs also? Directed graph?
No, we have not started with directed graph yet.
How different difficult that would be?
So with directed graphs, what can happen? So here, if we just think about the fundamental idea of this model is that so one missing edge can start one group and the other group are free. Of course, there are various things. One missing edge can start 2 groups also. We are taking care of those. There the algorithm is used. But if you think about directed graph, you don't require missing edges to start one group. So that will add further difficulty.
Okay, thank you.
Alright, let's thank Kaushik again. So the next talk is on computational power of mobile robots, discrete version. Abhishek Sharma is going to give the talk, and this is joint work with Pritam Goswami and Buddha Dev.
Hello, this is Abhishek Sharma from Department of Mathematics, Jadavpur University. Today I am going to present my work titled Computational Power of Mobile Robots, discrete version. So here we are dealing with a group of simple, inexpensive mobile computing units. This can be anything. You can imagine this as simple, tiny sensing devices or large size robots which are deployed over a region or continuous region or plane or any network or in any graph with some goal to solve some complex tasks collaboratively. For example, like maintaining some network or rescuing or security purpose or patrolling some region or cleaning. Okay. So in this line of research, the main goal is to find the minimum capabilities these robots are required to complete one certain task. Okay. So in this research, some of the fundamental tasks that have been widely studied, these are gathering, exploration, dispersion, pattern formation. From the name you might be able to guess what is the goal of this works. Like gathering, here the goal would be to gather all the robots at a certain point. Okay. The basic robot model, if we look at, the robots are decentralized, they are autonomous, there is no central control, they have no unique ID, and they look same from the outside, they are identical, they all run the same algorithm, they are homogeneous, and they are disoriented generally. That means they don't share any common notion of direction with others. Okay. So how do the robots work? Say they operate in loop compute move cycle. Okay. So let's consider these black dots as robots and focus on this one. So on activation, first it enters into the loop phase where it takes an atomic snapshot of the surroundings, and by that I mean finding out the position of the other robots with respect to its local coordinate system. And then it enters to the compute phase where it runs the inbuilt algorithm and finds out the position, and next it enters to the move phase and moves to that computed position. Okay. So here, based on memory and communication ability, there are four main models which we are going to be focusing at. If the robots have no persistent memory or communication ability, then we say this is an oblong model, that is the abbreviation of
abbreviation of oblivious robot. If the robots have finite communication ability but no persistent memory, then we say FCOM model. And if it has only for finite persistent memory, then we call it F-star model. And if it has both finite memory and finite communication ability, then we say it's a Lumi model, luminous robots. Why I'm calling it luminous? Basically, because this is imagined as these robots have some finite colors, lights, persistent lights that can take finitely many colors, and these colors actually serves as a memory as well as a communication architecture for them. Okay. Next, scheduler. There are main two schedulers we all know. One is asynchronous and other is synchronous. If I consider this as the timeline, okay. So in asynchronous scheduler, the robots actually activate at any time independently. They do their phases, complete their phases independently. Okay, but in synchronous round, the time is equally divided into rounds, and in each round, the activated robots here I have only illustrated for 3 robots, R1, R2, R3. So the activated robots simultaneously do their phases. Okay. In fully synchronous is F-sync. All the robots get activated in each round, but in semi-synchronous, some robots might not activate. Okay. So based on these 4 models and these 3 schedulers, we can consider one variant having model M and together with the scheduler K. So we are calling this as a variant. So combining these 4 and 3, 4 models and 3 schedulers, we can have 12 different variants. We are actually going to compare the computational power between these 12 variants. Okay. First, let's look at some definition before moving on. So by M in parenthesis K for a model M and scheduler K, we denote this as a problem set, a collection of problems, where a problem belongs to this set if this problem is solvable in that variant. What do we mean by a problem in this regard? A problem is a finite or infinite sequence of patterns made by the robots with some restriction together with some initial set of valid set of initial patterns. Okay. And when do we say a problem is solvable in a variant MK? If there is an algorithm such that for any execution of that algorithm under a scheduler K, each pattern of that problem is formed in that given order in the problem within finite time, starting from any valid initial pattern which is specified in the problem. Okay. Next, the definition of these comparisons. So we say one variant M1 K1 is greater than equal to or not less powerful the other M2 K2 when the problem set, this problem set for this variant M1 K1 is contains the problem set of the other one. That means any problem that is solvable in M2 K2 is also solvable in M1 K1. So then we say it's not less powerful. Okay. And for strictly greater than, you can have the idea that any problem that is solvable in this variant is also solvable in this variant, but this is strictly powerful. That means there is some problem that is solvable in M1 K1 but not in M2 K2. Okay. Next is computationally equivalent. That we say 2 variants are computationally equivalent if any problem that is solvable in this variant is also solvable in that variant and the other way around also. Okay. Next we say 2 variants are computationally or incomparable or orthogonal if basically none of the problem set contains the others. Basically that means there exists one problem which is solvable in this one but not in this. There exists another problem in P2 which is solvable in this one but not in this one. So they are kind of parallel variants. Okay. So this model comparison for continuous domain. By continuous domain means that when robots are operating on Euclidean plane or on continuous circle or a continuous line. So for this part, in this 4 works, earlier works, this complete comparison has been done already, and they have considered full visibility. That means each robot can see all other robots that is present in the system, and they have considered unobstructed visibility. That means the robots are transparent. One robot does not obstruct the other's visibility. Okay. Next, in these 2 works, in the first one, they have considered opaque robots. That means obstructed visibility. They have considered this model comparison, and in this one they have considered limited visibility, where a robot may not be able to see all the robots present in the system. It can see up to certain distance. Okay. In the continuous domain, some of the very interesting result that actually motivates us to do the same for the discrete version. You see, the first one says that LumiF, that means luminous model with fully synchronous. This is equivalent to FCOM, the finite communication with fully synchronous. That means if we have finite communication with fully synchronous scheduler, this is as good as having memory, finite memory. So this is computationally equivalent. Here, this result gives us luminous asynchronous is equivalent to luminous semi-synchronous. So if we have finite communication and finite memory, then the asynchronous model is as strong as semi-synchronous model. So this basically motivates us to see what more we can or different we can get for the discrete version. Okay. So in the discrete version, it's a different. The basic thing is we have a graph. Okay, but either in the plane or you can imagine anywhere, where the robots are initially placed on the some nodes of the graph, and the robot can only move from one node to another node that is adjacent to the previous one, only following the path that is connecting these 2 nodes. And a robot cannot rest on edge. It can only rest on some node. Okay. There are some there's series of works that has been done in the discrete version also, and I just listed some of them. So now one can wonder that we have the full comparison for the continuous setup. So maybe the same results will follow for the discrete version, but that is not necessarily true, because there are some fundamental differences. Let's say in the continuous domain, the robots we can direct a robot to move at any infinitesimal precision in any distance. We can ask them to move. But for that reason, they have considered some problems like point convergence, where the robots are required to converge at a point. So these kind of problems cannot be considered in the discrete domain. Next is lack of information. Okay, when a robot sees in a snapshot, another sees another robot, it cannot distinguish whether the robot is actually in a way of is moving or still. It cannot say. But in the discrete domain, if a robot is seen on the edge, you can say no, it is moving. It's not still. So there are some fundamental differences. That's why the results completely do not follow from the continuous domain. So in the discrete domain, actually there is only one word that considers only the 2 model, Oblard and the Lumi model. So we want to incorporate the other 2 extra. we want to incorporate the both the other two model, FSTA and FCOM as well, because we want to compare whether memory is more powerful or communication is more powerful. Okay. So we have tried to fill the table for all the models except for this 5. So there's some trivial results. Since the fully synchronous is more strong scheduler, so it will have it, and the asynchronous is a more general one. So obviously we will have more problems that can be solved in the fully synchronous than asynchronous. So this first one for any model, this is not less powerful than synchronous, not less powerful than asynchronous. Same for any scheduler, the Luminous model has both memory and communication, but for Oblot there is neither persistent memory nor communication. So this is the weakest one. So and FSTA has only memory and FCOM has only communication. So obviously this is the in hierarchy is stronger and this is lower in the hierarchy, as far as computational power is concerned. Okay. So from the previous results, we have I mentioned it earlier. So actually this first result, LumiF is equivalent to FCOM, that was in the continuous setting, but in the proof they have done, this also follows for the discrete domain as well. And this one is done in this work, the LumiS is equivalent to LumiA for discrete domain as well. Okay. So here we have considered 4 problems, and through these 4 problems we have filled that table. Okay, so I will not talk of all the problems on the time. So just look at the first problem, the move-ons problem. Here we have considered this 5-node graph where 2 robots are placed on these 2 nodes, and the problem asks the robot, this robot only to move once and settle down at this node and not move further. And this node, this robot, this problem asks this robot to stay still forever. Okay, so this is a very simple problem. Okay, but this is well designed so that this problem can only be solved if the robots have finite memory, that is FSTA. Okay, the scheduler can be as general as asynchronous, but it cannot be. It cannot be solved in fully synchronous Oblot. So scheduler doesn't help if there is memory, and if you do the communication also, it's semi-synchronous. It cannot be solved. So there are more 3 problems. I am just skipping it. So considering these problems, we could fill the table except for this 5. Okay. So here we can see this one is from the previous result that FCOM-F is equivalent to LumiF. So that's why we have these 2 tables columns are same. Then we have this LumiA is equivalent to LumiS. That's why these 2 rows are same. Next, in this work we have shown that FSTA-A and FCOM-A is computationally orthogonal. FSTA-S is computationally orthogonal to FCOM-S, and FSTA-F is computationally weaker than FCOM-A because of this one, because FCOM-F is equivalent to LumiF. Next, next we have this one. LumiA is strictly this though I have the LumiA is computationally equivalent orthogonal with FSTA-F and stronger than FCOMS, FSTIS, oblates. So Luminous is much powerful with even asynchronous scheduler. Next, we could show these orthogonalities between the models. And for the future work, basically these 5 are still open. Just if I look at these first 3 here, for the continuous domain, actually these greater than equal to is the true. But in the discrete domain, it is still open. It can be equivalent also. And if it is equivalent, this will be a very interesting result, because the asynchronous or semi-synchronous are equivalent in discrete domain, whereas in continuous domain, the asynchronous is weaker. Okay. And for future scopes, we can incorporate these results are for full infinite visibility and unobstructed visibility. We can incorporate the limited visibility model and obstructed visibility model also. And other communication models we can also consider, like whiteboard communication models or local face-to-face models, which are widely used also. Payment model or robots. Here we have only said robots with finite memory. We can also incorporate robots with infinite internal memory, where we can have robot with IDs. Okay, so future scope we can have a comprehensive model comparison considering all these scenarios. Thank you.
Let's thank the speaker. In the interest of time, let's have the other speakers set up while we take questions. Any quick questions? Okay, let's thank you. Okay, so next we have 2 short talks, both by the same author, Raja Das, who will first speak about rectangle enclosed triangle grid exploration with myopic luminous robots. And let's wait for him to get started.
Good afternoon, everyone. I am Raja Das from Department of Mathematics, Jadavpur University. My presentation is about rectangle enclosed triangular grid exploration with myopic luminous robots. This is joint work with Pritam Goswami, Pratik Mandal, and my guide, Professor Buddhadev Shah. This is the outline of the presentation. What is exploration? Next, what is rectangle enclosed triangular grid? Then robot model. Then we have 2 algorithms, and after that the conclusion. So exploration in a graph network means each node of the graph has to be visited by at least one robot within finite time. And there are 2 types of exploration. One is terminating, so the robots will terminate when the exploration will be achieved. And another is perpetual exploration, where the exploration will be continued. So this is an infinite triangular grid where we can consider these lines as columns. So actually there are 3 family of parallel lines. So this is one family, and this is another family diagonal, and the vertical one is another family. we have to put a rectangle in the infinite triangular grid such that a pair of parallel sides of the rectangle align with a family of parallel sides of the triangular grid. Then consider the nodes which lie on or inside the rectangle. Then the graph will be induced by those nodes is called the rectangle enclosed triangular grid. Depending on the degrees of the corner nodes, here it is 2 degree, but here it is 3 degree. So depending on the degrees of the corner nodes, there can be 6 type of rectangle enclosed triangular grids. So our aim is to provide some algorithm by so that the robots which are present on that RETG will execute the algorithm and each node of the RETG will be explored. So the robots are considered myopic, that means they can see up to a certain hop distance. The robots are equipped with light, luminous model robot. Scheduler is fully synchronous. There is no axis agreement. And in one algorithm, we have considered fixed chirality, and another algorithm requires the common chirality. So first algorithm 1. So this is one of, we have considered here the visibility range as 1. So a robot can see up to 1 hop distance depending on the degrees of the nodes. So these are the possible views of a robot. So initially 2 robots can be anywhere of the RETG, but they must be on adjacent nodes. And one robot with color L or R, we call that robot as leader robot, and another robot with color F, and it is the follower robot. So as an example, we have considered this RETG. Here this has 1, 2, 3, 4, 5, 6, 7 columns, and on the third column we have considered a robot with color L, and in here it is a robot with color F. So the basic idea of the algorithm is the robots will move together here, then it will explore the column 2, then column 1, again it will enter the RETG through column 3, then column 4, 5, 6, 7. So in that way it will be explored the RETG perpetually. So this is the movement. Next, algorithm 2 is almost similar like algorithm 1, but here the visibility range we have considered 2 hop view. So a robot can see as these nodes only. Here initially the robots can be anywhere of the RETG, provided that they must be within 2 hop distance. That means they can be at 1 hop distance from each other or at 2 hop distance from each other. One of the robots with color L and another is with color F. In the previous algorithm, we considered that the leader robot is with color L or F, but here we have considered only one color. We have reduced the number of color, but we have used the distance as instead to reduce the color. So as a conclusion, algorithm 1 requires visibility range 1, number of robots here require 2, and number of color of light is 3. In algorithm 2 requires visibility range 2, number of robots is 2, and number of color is also 2. So these were the 2 algorithms of this paper. And as future, these algorithms work under synchronous scheduler. So as a future work, algorithms for asynchronous scheduler can be thought. Thank you.
Thank you, Raja. Any quick questions? set up the next slides. The next talk will also be by Raja, and it will be on exploration of infinite triangular grids by myopic robots without chirality.
This presentation is about exploration of infinite triangular grid by myopic robots without chirality. This is a joint work with my guide, Professor Buddhadev Shah. So, as we know, exploration means each node of the graph has to be visited by at least one robot. So, we want to give the algorithm so that the robots which are present in the infinite triangular grid will execute the algorithm, and together they explore each node of the infinite triangular grid. Here we have considered also myopic robots. Robots can see up to certain distance. Robots has light, the luminous model, and scheduler is fully synchronous. There is no axis agreement, and here we have considered no chirality. They do not share any common chirality or any other chirality. So here the visibility range is also 2, and different 2 of views depending on the orientation of the robot. So in a round, robot can label its neighboring node like the left one, and another round robot can label its neighboring nodes like the next figure. So this is an infinite triangular grid. Initially, these five robots are needed. So 2 red robots, 1 green robot, 1 violet robot, and another is blue robot. So 2 red robots must be on adjacent nodes, and a green robot at 1 hop distance from each red robot. The violet robot is at 1 hop distance from a red robot and green robot, and the blue robot at 1 hop distance from the red robot and the violet robot. So we can think the infinite triangular grid as union of triangles. So the smallest triangle is T1, the next triangle as T2, the next triangle as T3, and so on. So in this way, each node of the infinite triangular grid will be covered. Now we have named the topmost node of a triangle Ti as Vi B0, the leftmost node as Vi C0, and the bottommost node as Vi A0. So what is the GRR configuration on Ti? If the topmost node of the triangle is occupied by a red robot, and the leftmost node also occupied by a red robot, and the bottommost node is occupied by a green robot, then that configuration will be called as GRR configuration on Ti. So this is a GRR configuration on T1. In the next presentation slides, we will see that how GRR configuration on T1 will become GRR configuration on T2, and the robots, blue robot and violet robot will explore the nodes of T2. And in general, how GRR configuration on Ti will become GRR configuration on Ti plus 1, and the nodes of Ti plus 1 will be explored. So it is a GRR configuration on T1. So from here, the robots will form the GRR configuration on T2. So this is the movement of the robots. So this configuration is GRR configuration on T2. Basically, the red robots are green, and green robots acts as landmark, and the blue and purple violet robot explore the triangles. Now, to make a GRR configuration on Ti to a GRR configuration on Ti plus 1, these red robots has to be shipped from here to here. So how it will be? It is on the topmost. This red robot is at the topmost node of the triangle. So how it will be go from here to here? So this is the process. Now these two robots, blue and violet robot, will move straight and towards the another red robot which is at VIC0. So after reaching near that red robot, this red robot will have to move from here to here. So, and finally, these two robots, blue and violet robot, will move towards straight to the green robot. After reaching near the green robot, here the green robot has to move from this node to this node. So, by shifting the three robots, two red robots and one green robot, the GII configuration on Ti+1 has been achieved, and all the nodes of Ti+1 also has been explored. So in this way, each node of the infinite triangular grid will be explored. So in this algorithm, we have considered visibility range 2, and number of robots required is 5, and we have used 4 color of light. And future work, optimality test, so that can we decrease the number of these parameters by maintaining other parameters, it can be thought. And algorithms for oblivious robots, here we have used luminous robots, but algorithms for oblivious robots can also be thought. Thank you.
Thank you, Raja. And are there any questions? If not, let's thank Raja and all the speakers of the session once more. And there are some announcements related to lunch.
Thank you all for attending the session. And lunch is now available on the 4th floor of the guest house. Please have it, and please gather again at 2 p.m. for the best of session.